Hi, Michael Birnbaum here, and this is going to be a little workshop on the recipe design and some programs that help you work with it. That's a design for the study of multi-attribute judgment, information integration, or situations where people combine information to form an evaluation, a judgment, or possibly to form an intention to do behavior. So let me show you the computer resources that I've developed in a website. Here's a page, a web page with computer resources for implementing the recipe design for weights and scale values in multi-attribute judgment. Um, Here is the link if you want to make a note of that. And I'm going to go over today briefly how to use the main programs that are here. The first one is Recipe Whiz. Recipe Whiz is a web page that contains a JavaScript program. So it's a web page that creates web pages for the collection of data online where the trials are constructed from a recipe design, put in random order, and it creates a output. It's a web form that sends data to a generic CGI script that'll save the data. So let's take a look at Recipe Whiz. It's a little big, so I'm going to shrink the screen size a bit so it all fits on here. And to get started using it, you just select some text in here. First thing you see is experiment name. And so I'm going to set up a little experiment on the problem of factors that might affect a decision to accept the COVID vaccine. At the time I'm making this, COVID was a pandemic viral infection that was killing, well, it had killed about 240,000 Americans, and about 4% of those were known to have it, were killed, and it was especially bad for people my age and older. So I'm going to type in here the title. I'm going to do a little experiment on that. And we're going to study the effect of price, risk, and effectiveness. So let's type in a title here. We selected the experiment name, and I'm going to type in, will you take COVID-19 vaccine? This text can contain spaces, and it will appear in the form that's created. And I push the computer's tab key, and that selects the next one, which should be the experiment's short name. And I'm going to call it vaccine. I'm going to use an underscore because there should be no spaces in here. This is going to be a variable that's going to appear in the file that helps you keep track of how the data got there and what study this is. And then you can go through and you can enter the names of the factors and the three factors that are sometimes called factor A, B, and C, or they might be called row, column, and layer. So we'll call them A, B, and C, or you get to call them the names for your particular experiment. In this case, price, and price is going to appear in bold. So you can enter HTML directly in here to change how it's displayed. And the B factor is going to be risk, meaning what are the dangers of taking the vaccine? For example, do you get a sore arm for an hour afterwards? or do you get a fever that lasts 2 weeks, or are you at risk for strokes or heart attack? And then the third factor, C, is going to be the effectiveness, meaning if you take the vaccine and then you're exposed to COVID, what's the likelihood you'll become infected? And the number of levels of A you can specify, and here I've said it there, the preset values are you can go with to explore the program. In this case, there are going to be three prices, 4 levels of B risk, and 5 levels of effectiveness. And then you get to enter the levels of price, and I'm going to include here high price, medium price, and low price. And I put them in order, just it's not required, but it'll help you keep track of your study if you make these increase from 1 to the number of levels. So high price is not good and is not likely to make people take the vaccine. So I put it first, high price, medium price, and low price, that's the best. So I have it in the third position of the 3 levels. And there are 4 levels of B, the second factor, and those are very high risk, that's bad, slightly high risk, slightly low risk, and low risk, that's the best. And there are 5 levels of the layers, C, and those are very low effectiveness, moderate effectiveness, high effectiveness, and very high effectiveness. These are going to be defined in the instructions. I'll show you that later. And then you can vary the preliminary material, and that is the HTML. BR is simply a line break or line return. And the separator, using the tab key here, separator between factors, again, will also be just a line return. And then you can put in after material. This could be HTML for images, or it could be anything else that you want it to be that's going to appear on each trial. Then you can change the number of buttons in the response scale, and this is going to set it up with a Likert type response with buttons that a person can push, and they'll be labeled at the left end, and you can type in here with very, very unlikely to very, very likely, because the dependent variable, the judgment, will be how likely would you be to take the COVID vaccine, a new COVID vaccine, if the price was low and it had a very high risk of side effects, and if it was very highly effective in preventing combinations like that. If you push the make the form button, it creates the HTML, and it's created all of the trials, and we can look at the HTML. You see here is something that says put your instructions here, and later I'll show you putting your instructions there. If you know HTML, you can modify this. You can also display the form. So pushing display the form, and I'll increase the size to take a little better look at this. This is how the form looks so far. Instructions for will you take the COVID-19 vaccine? Instructions will go here. There'll be warm-up trials. And the program presets 4 warm-up trials for you, but you can edit that and add more. I recommend that you do. And then the trials appear here. So here's one for, suppose the price is medium and the risk is slightly high risk, and the person can push buttons to say whether they're very, very unlikely or maybe 50-50 up to very, very likely to take the vaccine given that information. And here are a number of cases. Here's one with very high price, very high risk, but very high effectiveness. And the person might make a rating there. And then at the end of the questionnaire, we have some preset age and gender and years of education and nationality, and there's room for comments. And you could add additional questions. And I'm going to just make a mark here to keep track of that it's just a test. Then you push the finished button and it sends them to a CGI and the data are being stored on a server. Back to the Recipe Whiz program. I showed you how to make the form. If I press make the form again, that creates another random ordering of the same trials. Push it again, it makes another random ordering. So I could make a vaccine 1 and a vaccine 2 or various other things I could do to create different random orders. I showed you what display the form does. Save button says to save, you must copy the HTML to a text editor. If I click OK, then it has selected all the text that were in the box. I can go Control C on my computer, which copies all of that text. I can then open up a text editor like TextEdit for the Mac or Notepad or various other editors that allow you to edit HTML. But a simple text editor will do. And I can go Control V and paste that text into this box. And then I can save it with an extension of .htm or .html and put it on the web and then recruit people to visit that site and they can fill it out. Of course, I would want to edit it first and change the instructions and maybe modify some other things in there. So I won't save it right now, but I've saved one with the name vaccine.htm. I'm going to delete that one. And I'm going to show you, here's one that's been named vaccine.htm, and it's already residing now on the web at this address. And here are some instructions. It gives some background on the COVID virus. It explains that the task is to judge how likely they are to accept or to take the COVID vaccine. Because at the time of creation of this study, there were no vaccines and no treatments for COVID. And the issue was, would people take the vaccine? It was also a time when people didn't trust the government, where the CDC, the NIH, and the FDA had lost some credibility because the government was promoting hydrochloroquine, which proved not to be effective, and various other treatments that were not effective, and was pressing for the issuing of a vaccine before an election, and people weren't sure whether they wanted to take it. And then there were various disinformation campaigns on the internet, and there were anti-vaxxer groups and various other people warning people not to take the vaccine. If a vaccine is going to be effective, of course, you want a large number of people to take it so that the vaccine ceases to circulate in large numbers. At any rate, so the dependent variable was, will you take the vaccine? Based on the independent variables, price, risk, and effectiveness. And it explains that the price refers to the amount you must pay out of pocket to receive the vaccine. The levels of price are low price, $20, medium price, $400, or high price, $10,000. Now I could have put directly into the form 20, 400, and 10,000, but I want to illustrate here that you can create descriptions that are explained in the instructions. Risk, here's a case where you really want to do that. Risk, low risk is described as 5% of the people got sore arms. This description could have been longer to describe all the risks for what we mean by low risk, but we're keeping it short here. And we could have typed that in and it would have appeared in the questionnaire, but instead it's simpler for people to read a short description than have to read this over and over again, this longer description. Slightly low risk meant 10% of the people got fevers and headaches for 2 weeks after getting the vaccine. Slightly high risk is 5% of the people got damage to the kidneys. And very high risk is 1% of those tested had heart attacks, so that's pretty serious. It doesn't explain whether the damage to the kidneys was such that you need dialysis, but that should have been probably included in here, how much was the damage. And then effectiveness refers to, it explained here, refers to how well the vaccine worked to prevent COVID-19 infection in the people who were exposed to the virus in the clinical trials. So what percentage got sick after they were exposed? Well, very low effectiveness. It's just 50-50. You have 50% chance of getting sick given you're exposed, a 40%, a 30%, a 20%, or a very high effectiveness, you only had a 10% chance to get sick given you've been exposed. And I've also increased from 4 to 8 so that the worst case, here's high price, very high risk, and very low effectiveness. Would you take that? Presumably people should be more unlikely, closer to on the unlikely end of the scale. Here's one that's low price, low risk, and very highly effective. And presumably people would be toward the higher end of the scale for how likely they'd be to take this example. So this is the worst and best of cases. And then there's some examples with based on a single piece of information or based on 2 pieces of information. So each of the 2 kinds, and then another with 3 pieces, just to give a kind of representative warm-up. And then come the trials, and the trials look the same as they did the last time. Now, when you push the submit button, the data go to a data file, and they appear, they're saved by a CGI that's explained in another package that I have on the web. It's in a chapter by Birnbaum and Ripes, and there's another chapter by Ripes and Birnbaum with the same information. And in that chapter, there are lots of other, in that website for that, there are a lot of other resources to go with that chapter, including the information on how to install the generic Perl script that takes the data and saves them in Factorial Design. I'll explain in the recipe design, which is a union of Factorial designs. I'll explain it a little more in a bit, what that design is. And here's a case where I actually took it seriously, and it saves the short name that you typed in, the date, the time on the server clock when it happened, the IP that it came from, the age and gender, 74 years old and male, and 20 years of education and nationality. And these, there are a couple of spaces here that are left for future questions a person might want to add to that. And then starting here in column 12 are the responses that were typed in. If the person clicks at the very low end of the scale, at the very, very unlikely, it's scored as a 1. And each button adds an integer to that. And there were 11 points on the scale, so the largest response could be an 11. And let's see, I hear a 10 in the, looks like I don't see that I used any 11s on there. So that's how the data are going to appear. Going back to the programs that are available. Make that bigger again. There's Recipe Whiz, and I went over the example study that was created with it, showing entering the instructions and a little modification of the warm-ups. Here's a program, Recipe Sim. Make that a little bit smaller. Recipe Sim is set up similarly to Recipe Whiz, but whereas Recipe Whiz creates a questionnaire that will run online that you can collect data online, Recipe Sim creates data according to a theory. And the theory is the averaging model. This one uses the relative weight averaging model that was popularized by Norman Anderson, and there are also some papers on this approach by Kent Norman and by me back in the 70s. And the simulation program implements the relative weight averaging model. I'll say a little more later about the configural weight averaging model, which is slightly different, but as we can consider the empirical data to be an approximation containing an important exception of configural weighting, but there's a lot to learn about relative weight averaging model, which is the one in which the weights are constant, but depend on the set of information that's presented. So we can again put in the project name. Will you take the COVID-19 vaccine? And we can give the short name here, vaccine. I'm going to add here sim to it because this is going to be simulated data. And we can have 100 simulations or 1,000 or whatever. I'll make it just a little smaller number for now. And tabbing through, we can enter the row, column, and layer names. And there are again price, risk, and effectiveness. So these are the defaults. You can type in other factors and replace them. And again, now we can specify the weight or the importance of the factors. And so just to illustrate, I'm going to put in weights of 2, 3, and 1 for these factors. So 2 for A, 3 for the weight of B, 1 for the weight of C, and then we're going to put in how many levels are there. There were 3, 4, and 5. And then using a tab key, that brings me to put the levels in for A, or you can click in and just replace, select and replace. And I put in some values, just numbers between 1 and 11 to get started, increasing numbers that I use. And then there's an initial impression, so W0 and S0, these are other parameters. Theoretically, S0 is the impression that would be created with no additional information. It's sort of like a Bayesian prior. It's sort of like a number that reflects what the judgment would be if the person was given no information. And the weight of the prior, or the weight of this initial impression, is an index of how resistant people are to changing their mind based on the information that's presented. It's also allowed that the that the response. Let me highlight this. The response is assumed to be a linear function of the psychological impressions, which are in this theoretical program are governed by the averaging model. So we have A times psi plus B plus error, but it's set up so that there's an identity function. So the multiplier is 1 and the additive constant is 0. Why do we want to allow a transformation response? Well, if you had some reason to know what the scale values were, but you had obtained them from somebody that did a study on, say, a 5-point response scale, and you want to predict what would happen with a 100-point response scale, you might want to put in the values you got from the literature, but allow the possibility that there's some transformation to get them into another scale. we don't think that the numbers of the response scale should be taken as absolutes. So let me explain what I mean by that. It's pretty easy to explain, usually with this joke. This fella asked his girlfriend to rate him on a 0 to 10 scale, to rate him as a lover. And the girlfriend says, 0 to 10 scale, I'd say about a 4. Well, a 4 is a pretty small number, so he felt pretty bad. So he said, how about on a 0 to 100 scale? She says, well, 100, 0 to 100 scale, I'd say about 33. And he felt better because 33 is a bigger number than 4. Now, if you get the joke, you laugh a little bit, or chuckled at least, because maybe 33 is not as good on a 0 to 100 scale as 4 was on a 0 to 10 scale. At any rate, the idea is that depending on the response scale you use, you're going to get different numbers, and these numbers aren't really unique. And so we're allowing, in your theory, the scale values to be on a different scale from the scale that the responses are on. So in here, they've been preset to 1 and 0. And notice you can also add error in case you're interested in how would statistical tests work with the recipe design. And so the error that's added is normal with a mean of 0 and a variance of sigma squared. And you get to change the value of sigma. And so in this case, we're on a 1 to 11 response scale, and we put in a standard deviation of 1. And so this is going to be normal distribution. So the error is going to be off by plus or minus 1 point on the 11-point scale. It'll be within 1 point on a 1 to 11 scale 68% of the time, and it'll be between 1 and 2 off about 13% of the time, and it'll be greater than 2 points off about 2% of the time, and off by more than 2 below about 2% of the time. Also, you can change the data rounding factor, and a 100 means that it will round the numbers to the nearest 0.001. Or if you wanted to add some granularity to simulated data, you might say, well, maybe the subject has in their mind a number like 7.62, but they might round that off to 8. So if you wanted to round it to the nearest integer, you could do that, which will add a little more granularity into the data. You can label the data, and that'll remind you the number of levels and what the names of the factors are. And we can simulate the cases. I had asked for 10. And you can push the save button, and that will select it. And again, you can copy and paste the data. I'll delete those and show what would happen if I simply simulate some cases. It's created column labels. We can save these, copy, Control C to copy, and then we can open up Excel, or you can copy them into a text file. And in this Excel file is called recipe sim, and they can be pasted in right here on the second page where you can enter the data. And here's 100 simulated cases. Let me open that program. Here's the latest version. I'll open it with Excel. There's a README here. And when we get to the data, notice that it's labeled the data experiment date, time, IP, age, sex, education, nationality. Here are the three that were left blank. And now is a good time to explain what is the recipe design. The recipe design is not a factorial design, but it's a union of factorial designs where each piece of information or each pair of pieces of information has been left out. So that means we're going to present A alone, and there were 3 levels of A, B alone, and there were 4 levels of B, C alone, and there were 5 levels of C, and we're going to present the A by B factorial design, in other words, price and risk with effectiveness left out. So the AB design, that's 15 trials there, 3 by 5 factorial design, and the AC factorial design, so that's price by effectiveness with risk left out, and that would be 3 times 5 or 15 trials. Let's see, the other one, the AB design would be 3 times 4, 12 trials, plus 15 trials, plus the B by C factorial design, which will be 4 times 5, 20 trials, plus the ABC design, which means 3 times 4 times 5 trials. And so the number of trials will be 119. And they've been placed here in the recipe sim output in the same order as they will appear in the data set from Recipe Whiz. So in Recipe Whiz, we create an online experiment, and the subject fills it out. Their data are going to come back in the same order. And what is that order? A1, that's A by itself, level 1. So that's high price. How likely would you be to take it if all you know is the price is high? Medium price or low price? High risk, maybe very high risk, slightly high risk, or low risk. And C is the effectiveness. Low effectiveness. Let me scroll a little to the right. Continue. I think you can see that now better, probably. So this is A1, A2, or A3. Then comes B1, B2, B3, B4. Then C by itself, effectiveness, the 5 levels. Then the AB design, the 1-1 cell. So this is in normal factorial order, where the rows are the first index, the columns are the second index, and the last index moves fastest. So 1-1, 1-2, 1-3, 1-4, 2-1, 2-2, 2-3, 2-4, 3-1, 3-2, 3-3, 3-4. Now the AC design, 1-1, AC 1-1, AC 1-2, AC 1-3, AC 1-4, AC 1-5, 2-1, 2-2, 2-3, 2-4, 2-5, 3-1, 3-2, 3-3, 3-4, 3-5. Then comes the BC design. Then comes the ABC design, all 3 pieces of information, the 1-1-1, the 1-1-2, 1-1-3, 1-1-4, the 1-1-5, the 1-2-1, 1-2-2, 1-2-3, 1-2-4, 1-2-5, 1-3-1, 1-3-2, 1-3-3, 1-3-4, 1-3-5. To understand factorial order, think about when you're putting gas in your car, which number moves fastest. The pennies move fastest, then they ring over, then the dimes move, then the dollars move, and so on. And so the last factor, like the pennies, that's the one that moves fastest. And it's the one that had 5 levels. So when it gets 1 to 5, then the next number clicks over. And so that's the ABC design all the way up to the last one will be A3, 4, 5. Let's see, it's coming here. There's the last one, ABC A3, 4, 5. Why 3, 4, 5? Because A had 3 levels, B had 4 levels, C had 5 levels. So 3, 4, 5 is the last set of indices for the ABC design. Let me go back to SIM a second, and then we'll come back to recipe. Back to recipe fit again. So now you know what the recipe design is. And recipe sim, now it's creating 100 cases. Takes a few seconds, and there they are. The rounding factor, save, I mentioned, allows you to copy and paste. So I think we did everything we need to do here. Maybe I didn't mention you can change the number of simulated cases. If you were going to have 0 error, you just want to look at predictions. Put 0 spread for the error. And just all you need to do is simulate one case because all 100 cases would be the same. And there you go. So we've now simulated one additional case. We wanted to save that. That's adding to the window, adding to the data that are saved in there. All right, let's go back to Excel here. So this is the page that has, so again, there's a README that says a few words about it. There's the data that you can paste in here. And this is where you could paste the data from the simulation program or from the experiment that's set up with RecipeWise. And here's the model is being worked out on this worksheet. The worksheet that is labeled calc. Let me increase the size here again. Make it a little bit bigger even. First off, the variables are numbered starting with V1 to 119. And they're labeled here A1, A2, A3, B1, B2, B3. And these are the means from the other page. So the means were calculated and then they were copied linked, and they're linked here. So if you know Excel, you can see that these have been linked from the other, from where I calculated the means. Instructions on how to work with Excel, including what I'm about to do here with the solver, are in my book, Psychological Experiments on the Internet. And I've got several chapters there going over how to fit models using the solver in Excel. You can do quite a bit with this worksheet, with this workbook, even without the solver, but if you install the solver, then you can fit your data to the model and get a best fit solution and this one's set up for 3x4x5. And if you learn about Excel, you can learn how to fit just about any model with just about any set of data using the solver. The solver is a very handy part, but it doesn't come pre-installed in Excel. At least I haven't seen it done that way. And in the various versions of Excel that I've seen, you search till you find the add-ins, and then you have to click a box and go through a procedure to add it in to your copy of Excel, to your installation of Excel. As I say, it doesn't seem to come pre-installed, but it's in the add-ins and you can add it in. So now we're just looking at what happened. These were the means. They were calculated, and then they were copied with a paste link here, so that this is the mean of the cell A1, this is the mean of cell A2, and this is the mean of cell B1, which is the judgment of based only on risk for the highest level of risk. This one is for the highest level of price, highest level of risk. This one's for the lowest level of effectiveness. For the highest level of effectiveness, C5 is a much higher judgment, 9.9. So as you increase the effectiveness, you increase the judgment. And they were put in order so that the judgments would increase, which just helps you keep things straight. It's not really required. Now, this number right here is the sum of the squared differences between the data and the theory. And the data have been copied over here, arranged in their designs, and corresponding to the data are predictions over on the right side. So here on the left side, we have data, and over here on the right side, we have predictions. And the data is 4.5, 7.08, and 9.2. And the predictions over here are 4.5, 7.09, and 9.3. They're pretty good. And so the A alone, the B alone, C alone, those are the data. The A by B factorial design, the A by C factorial design is here, and its predictions are over here. I have to scroll over to show them to you. And the sum of squared differences between this matrix and this matrix are included here. So in these tinted sort of, I don't know if you want to call that a pink or slightly orange, maybe a flesh, some kind of flesh color. They've been copied over. And so those measures of fit in each matrix have been added together, and they're here in this cell. And these are all the parameters. So W0, and when you work with Excel, you'll learn that you can name variables. You can give them theoretical names. So this is W0, this is S0, this is the weight of A, this is the weight of B, this is the weight of C, and so on. And so these are and I've also labeled them in this column here. These labels have no real function. They help me keep track of what these variables are. What really counts is what's up in this box. And you notice I named W0 as W0 with an underscore, and that helps keep you from giving a variable a name like BC, which might be a valid column reference, or B1, that's a column reference in Excel. So if I had something I wanted to call it B1, I would call it B1 underscore, which will keep me from confusing myself in Excel. And so these are the parameters, and I've colored them in yellow. And then to fit the data to the model, you click on the cell you want to minimize, and then you go to Tools, and you get the solver. Now, depending on what version of Excel you have, the solver may not be there. You might have to add it in. And where it goes in these menus and lists, this is how it is on the Mac for this version of Excel. But it may appear in a data, in your data thing, and you may be able to move it around where the solver appears. But I come down here and I select the solver. And then I check that this cell corresponds to the cell that I want to minimize. Notice that it's also highlighted. I need to click, what do I want to do to the cell? I want to minimize it. I don't want to set it to a value. I don't want to maximize it. I want to minimize it. And then you get to choose which cells do you get to change. So it will adjust the value of these cells. So you can select what's in here. In this case, I'm going to select the things that the program will change. And so they now are highlighted over here, and they're listed in here, and you can also use this feature to search your web book, your workbook. We can put in constraints. For example, if I want to constrain the parameter to a fixed value, or if I want to keep it in a certain range, I can add constraints. And so you can edit and put constraints in here. Which minimizer you want to use, you can select. There are some options here. And again, how to work with the solver is explained in another book. We click the solver button, and then it will vary these parameters. Notice the numbers are changing a little bit. And this was already a pretty good solution. And the sum of squares is 1.01. And so I get a choice of keep it or restore the previous values. I'll click OK. So that's working with the solver. And again, there's more information on that elsewhere. The marginal means for A, in other words, the effect of A alone, the marginal means of A averaged over levels of C. The marginal means of A averaged over B, averaged over A is the red line and the red dots. And incidentally, the symbols or the markers are the data and the lines are the theory. And I didn't add that much error. I had a standard deviation of 1 and 100 subjects. So you'll notice that the simulated data fit the model that they were based on pretty well, and we shouldn't be too surprised about that. But this helps you understand what it would be like if your data were constructed by this theory. It helps you understand the theory. You could also put data in there, empirical data, and you'd see how well the theory does for your empirical data. According to the theory and the Zen of weights, to know how important a variable is, you don't look at the effect of that variable. Now that's counterintuitive to a lot of people, especially if they've studied analysis of variance or multiple regression, because when people study multiple regression, they calculate beta weights. And the bigger the beta weight, supposedly the more important the variable, more of the variance that it accounts for if you multiply that by the variance of the variable. The more relative of the variance, the relatively bigger effect it's supposed to have. But at any rate, all that lore of multiple regression does not apply to averaging models, which have been shown to be empirically more accurate descriptions than additive models like multiple regression. Now, people that have studied multiple regression, they always get it as a data fitting device, and they don't necessarily think of it as a model. So they're a bit confused about testing the regression model and rejecting it as a theory of how their data came about. And so people who use regression get themselves confused. So you have to forget everything you learned about regression when it comes to talking about the weights and scale values in an averaging model. Instead of thinking about a variable is important if it has a big effect, think about this. Variable is important if another variable has less of an effect when it is presented. And so when we look at the effects of A, and these are the effects of A by itself, A averaged over the levels of C, and A averaged over the levels of B, and A averaged over levels when both B and C have been presented. But these are all effects of A in the different designs. Instead of thinking how big is the effect of A as telling me anything about the importance of A or the weight of A, I look at the effect of A to understand whether B or C is more important. That's the Zen of weights because it's counterintuitive to a lot of people. The less the effect of A when it's paired with, if A has less of an effect when it's paired with B than it does with C, and that's what happened here. A paired with C, that's the blue triangles. There's the slope or effect of A. That's price again. So the price is manipulated and we're seeing the marginal means. When A has been presented with C, it has more effect than when it's presented with B. So B has a greater weight than C. So we look at the effect of A to compare the weights of B and C. And from the results here, we have learned that B has greater weight than C. This graph, if we look very closely, this is the effect of B averaged over levels of A, and this is B averaged over levels of C in the blue, and it has less of a slope. So we see from before that B had more weight than C, and now we've learned that C has more weight than A, because the slope is less with C than it is with A. So if B has more weight than C and C has more weight than A, then what do we know about the next graph? We should be able to predict the relative slopes here. And indeed, that's what we find. Namely, B has a greater weight than A, because we found that B had more weight than C and C had more weight than A, so B better have more weight than A. And we should be able to predict this quantitatively as well, this difference in slopes. Again, this is C averaged over A, and it has a greater slope, so A is less important than B, and we learn that from the effect of C. That's the Zen of weight. We also get the graphs of the AB factorial design, the AC factorial design, the BC, and the model predicts that these curves should be linear and parallel when plotted against estimated scale values, which have been estimated in recipe sim. And so this worksheet does a lot of work for you if you have a 3x4x5 design, and it should have a great educational value for you if you want to use it to learn how to fit a model using the solver. And then you can fit any other design or any other kind of model using the solver. Let me come back to our resources and see what else is there. Those are the three main programming resources. And so we've gone over Recipe Sim and Recipe Fit. And here's some more good things. Here's a paper on recipe. And I'll keep updating this. So this is a working paper in which I explain what is the recipe design and what is the averaging model. And there's a little discussion in here of the Zen of weights with an explanation again about the slopes that I was kind of going over with you intuitively. Here we see the mathematics behind that. It's the fact that if the effect of A is inversely related to the sum of the weights of all the information. And so when B is presented, the effect of A is inversely proportional to the weight of B because it appears in the denominator. Or in the AC design, the effect of C, and the ABC design, in the effect of all of them. That's the one that had the least slope, and the effect of A by itself had the greatest slope. All those are implications of the averaging model. And then it talks about how to work with the programs, gives a basic introduction, and there are some references to some of the old classic literature. One of the things in the old classic literature is I first wrote a program in Fortran to do recipe, and it was called recipe because it was simply trying to set up a package to teach people about the averaging model in which they would be able to estimate weights and scale values. A factorial design by itself does not allow you to test adding versus averaging. It does not allow you to estimate weights and scale values. So I wanted to teach the students, what do you need to do it? There are designs that are less than recipe that will suffice to work. But I wanted students to guarantee to make it work and to guarantee to make it work with a lot of redundancy, which means you have a good test of the averaging model and you have a good test between adding and averaging models. So you test between models, but you can also have absolute tests of a model. So this program is included here along with some citations to the literature and some of the classic papers. One by Kent Norman is an important one, 76, and there's one by me where I wrote the program that eventually became Recipe for an experiment on intuitive numerical prediction. And some of the literature is reviewed in a paper by Birnbaum and Mellers from the 80s, and a nice chapter by Stevenson, Naylor, and Bussmeyer from, I think it's about 1990, that reviews a lot of classic judgment literature, including the recipe design and some of the studies that employed it and employed constant weight averaging or configural weight averaging models. And as I revise this paper, I will add something about the some of the complications that are introduced with configural weighting, which is more accurate than the simpler relative weight with relative averaging model with constant weight. Coming back, I've lost track of what's in. Let's see if we go back this way. There's also a brief video that's going to be that I made for the SCIP conference, Society for Computing in Psychology. And I'll be giving this talk, which because of the COVID pandemic this year is a virtual conference, and they had us upload videos. And so here's my video. It's just an 8-minute quick introduction that you can show your students. And if this video comes out, I will link it here as well at this same URL. All right, so with that, let me say thanks for your attention. I hope you found this educational and that you learned something about the averaging model, about the recipe design, and about the resources that are available to you. Recipe Wiz that enables you to create forms that will run on the internet. Recipe Sim that'll create data in the same format that you can play with the theory. I should mention that all of the programming is included in those single files, so that if you just view the source, you can see see everything that's all in one place. Then you can go in and edit it and change it around for whatever purpose you might want to have. So with that, anyway, thanks for your attention and for your interest in the work, and I hope you're able to put it to good use. So good luck in your research.